All right, so today's lecture is about randomized tree metrics. So this continues a theme of recent lectures about uh, metrics, starting with our lecture about dimensionality reduction, which was about L2 metrics and very explicit kind of Euclidean uh, metrics. And in fact, it was a question that I was asked in the back that motivated me to teach these other metric things. Last time we did sparsest cut. We also discussed Maxwell min cut, and that was about metrics that are embedded on the line. So either one line or a sum of lines. And it was also about certain graph structural observations and this very strong connection between cut metrics and cuts and metrics, and in particular line metrics. So there we had a relatively simple algorithm. We sort of rushed the analysis, but we had a relatively simple analysis algorithm that showed that you can take any metric and convert it to an L1 metric while losing a log n factor in the distances, which translated into a log n approximation for sparsest cut. Yeah, we didn't do too much background, but within the field of approximation algorithms, that's a very, very central result. So today's lecture will also be a very important important result in the field of approximation algorithms, but it's going to be about tree metrics rather than line embeddings. Okay. So, all right. I was going to erase this, but I forgot. That's all right. All right. So what are metrics? This was sort of implicit in some of our past lectures, so I'll just go over it quickly. It's any mapping where for any two vertices, I'm assigning a value. We have some simple rules. It has to be symmetric. The distance from point A to point B should be the same as the distance from point B to point A. That's not necessarily true. Sometimes going down a hill is easier than going up, but here it's symmetric. Things are positive, right? Distances are always positive unless it's point A to point A, in which case the distance is 0. And most importantly, we have the triangle inequality. The fastest way to go from point A to point B is at most the fastest way from point A to point C plus point C to point B. Okay. And of course, we often think of distances just on a map, but we're very creative in computer science and algorithm design. So we're not only interested in things like Euclidean metrics, but we're interested in, say, shortest path metrics or metrics that are induced by cuts. All these different things are actually connected to metrics that might not appear so kind of plainly geometric at first sight. All right, so there's a lot of problems about metrics. Let me just describe a few. Okay, so the first one I'm going to introduce is called buy bulk network design. So what's the high level idea? You are AT&T or something, and you're building networks, right, to connect America, right? And at some level, there's all these kind of point A and point Bs, and they have to be able to connect to each other. And maybe you know that Los Angeles talks to New York a lot, and Texas only talks to Seattle a little or whatever. There's different demands for different pairs and stuff like that. So you want to build out a graph that can connect the pairs, but also kind of, these these wires may have different capacities depending on how much communication is expected to pass through. Okay, so you're going to kind of build a network, and you're going to also maybe choose a path between every pair of cities or something, so that you're able to kind of route everything simultaneously. Okay, and then the question is, how do we do this cheaply or quickly or whatever? So let me give the formal setup for this particular problem. There's other network design problems, but here we're discussing this one called buy bulk. So the full input is, so you're given some undirected graph G, okay? And that sort of represents everywhere you could put the wires, okay? So there's lengths for every edge, like a distance between two cities. And you have demands between every two pairs of vertices. So just sort of how much they want to communicate with each other. Okay. And okay, so we're going to at some level sort of buy edges or buy capacity on edges. But what makes this a quote unquote buy at bulk network design problem is that we're going to have sort of an interesting cost function. So instead of just saying like, oh, one wire is like $10 per unit of capacity, we're going to do something a little bit more general and say, okay, for each edge, I have some kind of cost function f sub e that's sub-additive in terms of the amount of capacity I want to send through that edge. So if I want to send like 10 units of flow, I would pay f sub e of 10. Okay. And all you would assume in this model is that f sub e is sub-additive. So the capacity of 10 plus 20, or the cost of 10 plus 20 capacity on an edge, should be at most the cost of 10 plus the cost of 20 taken separately. Okay, so you're just assuming some kind of economy of scale kind of model. And nothing else beyond that. Okay, so not very much structure. Okay. Now, given this input, what you need to do is choose a path between every pair of vertices, every pair of cities. Okay, that's like sending all the messages along that path. Okay, and what's the cost? Well, I'm going to sum up for every edge E, the length of that edge, times the cost per unit capacity per unit length. So the capacity on the edge will be summing up over all the edges, summing up over all the pairs ST where E is in the path from S to T. Okay, so I'm summing up over all the pairs that are using that edge to communicate their demand. Okay, however much they're communicating. So that's how much I'm sending over edge E, given my choice of path per pair, and that plugs into my cost. Okay, which is some kind of something with decreasing marginal cost. All right, so that's one problem that people were interested in. Let me give you another example. This one you guys are most likely to have seen before. Something like clustering. Okay, so you're given a bunch of points in a space, and one way to summarize it is to sort of pick out a few. Sorry, my eyes are irritated. Pick out a few representative points. Okay, and say, oh, these, and just kind of group them. Right. So if you wanted to pick out, I don't know, if, let's say you wanted to pick out 4 representative points. Okay, so maybe like up here, there seems to be sort of like one sort of cluster of points or something, right? And I say, oh, okay, this is a good representative for all of these points. And then maybe, okay, there seems to be sort of a cluster down here of some kind. Yeah, I don't know what the right answer is, and just say, okay, this I'm going to think of as a representative for these points, right? And then, okay, maybe I would pick this one, and maybe this one. Okay. And I'll just assign the red points to the closest blue point. And say, oh, okay, this is a reasonable summary for these points. And this is a good summary for these points. Something like that. And so I might output like, oh, I don't know, I have roughly 1, 2, 3, 4, 5, 6, 8 of roughly this point, and 8 of roughly this point, and 6 and 8 or something, right? And whatever. It's a much smaller summary of the original point set. Okay. Other applications include in operations research kind of situations, you're trying to maybe build some kind of service. That service is a lot of people. So you can build like 4 gas stations, and you want it to be close to all the dots, so no one's too far away from a gas station or something. All right, so formally, The input just consists of a metric and a parameter k, and you want to choose k centers. And there's different ways to define a cost. So this is what's called the k median problem, where our cost function is summing over all the points, the distance from that point to the closest center. You want to minimize this. Okay. All right, so that's the second problem. How about a third problem? All right, metric labeling. All right, so I guess this comes up in image segmentation. But the idea is you want to break up the image into regions and that are presumably represent real entities. So you can see this person is highlighted in red and kind of separated from. It also realizes the street is sort of in purple and stuff like that. So you can see the segments. Okay. So what's one way to model this problem? So yeah, the typical way to model an image is you think of it as a big grid graph. So every pixel is a node and is an edge next to the neighboring pixels. And so the edge weight might be very big if the pixels are very similar, and very small if the neighboring pixels, have very different colors. Okay. And so the idea is you want to assign a label to every single pixel, some shade of color in this case. All right. And you have oh, interesting. Did I do that right? Okay. Sorry. Okay. All right. So you want to assign labels to every pixel, and you have a cost function that says, oh, if you assign this vertex, this label, you pay some cost. Maybe it's 0 for most of them, but maybe like you had someone go by hand and say, okay, this pixel right here should be a person. Like they'll just pick one pixel inside the person. Say that's definitely inside a person or something. This is inside of the street. So you can give like some prior knowledge with these costs. Okay. And we also assume, I have a lot of messed up notation. We also assume a metric on the labels. Okay, so we have some idea of which labels are more similar or less similar to each other. Okay. So the goal then is to assign labels to all the vertices. That minimizes the cost. So I'm summing over all the vertices of the cost of assigning this label to V. Okay. Plus, for every edge, the weight of the edge times the distance between the two labels. Okay, so if the weight of the edge is high, which maybe means the pixels are very similar color or something, and so we would think they're part of the same label, then we would hope that the labels are sort of similar as defined by this metric to make the cost go down. So we want that distance to be small. Okay, so that's one way to model this and set up segmentation. Okay. All right, so there's a lot of other problems out there, and I would emphasize this more if we were doing an approximation algorithms class. So, Steiner tree problems, task system problems, vehicle routing, placement problems, what's called the K-server problem, another Steiner tree problem, and so forth. Okay? So these are all just problems where metrics come into play prominently. So today's class is about tree metrics. Tree metrics just mean shortest path metric on a tree. Right? So why are these so convenient? Okay, well, let's take a step back. Many problems that we work on are like closely related to paths and graphs in some sense of the word. Even max flow is packing paths, and min cut is cutting up paths. Okay. So at some level, what makes max flow so tough, packing paths so tough, is that there's like exponentially many paths from S to T that you could be squeezing in, right? But in a tree, how many paths are there between point A and point B? One. There's no choice of path. Okay, so that takes a lot of these problems and makes them much easier. Okay. Maybe a simpler argument is just to look at how do you compute shortest paths in a graph versus a tree. Well, how long does it take to compute shortest paths in a graph with m edges and n vertices? All pair shortest paths. So if I wanted to n squared. So Floyd-Warshall is like n cubed. What if the graph is sparse, like m is smaller than n squared? What would you do? Well, I taught some of you this. No, that's flow. Yeah, you can just run Dijkstra from every vertex, right? That's simpler. Well, it's down here. Okay. But on trees, there's all these nice data structures, right? You can set up these things called linked cut trees and stuff like that. But the kind of query that you can do on a tree once you set it up is like, I don't know, you take this node and you say, what's the least common ancestor, right? Which would be this node here. And you can also ask questions like, what is the sum of numbers between this node and the root? And stuff like that. So if you can do something like that, then you can, and if I wanted the distance from those particular point A and point B's, right? Then we can do two of these leaf to root queries that'll just sum up all the numbers for us. And then we can do one more root to node query from that least common ancestor and subtract two of those, right? And then that'll get you the length of the path, right? So trees, you can just do anything as fast as you can, as fast as you want. Okay. All right. So what's the point though? A lot of these problems, which might have seemed complicated, actually become much easier for tree metrics. Okay, sometimes they can either be approximated easily or even solved exactly, right? Take, for example, buy a bulk network design, right? This one seemed like an awfully complicated problem, especially when you consider this crazy subadditive cost function. But if you're in a tree, there's no choice of path. You only have one choice of path between every pair S and T, right? So this problem would have been not a problem at all on a tree. Okay. All right, so what's the point of all this? So we're going to be exploring, focus on the top half first, sort of an algorithmic paradigm where we take as input some undirected graph. Everything we're going to do is on undirected graph, partly because that's when the shortest path actually give you a metric. If it's a directed graph, then it might not be symmetric, and that causes some issues. But you're given an undirected graph with edge weights for whatever problem you're interested in. And we're going to try to compute some kind of tree T that includes the original vertex set amongst the nodes, so that the shortest paths on T are close to, not T, but G, are close to the shortest paths in G. Okay? And insofar as we can preserve the distances, so I take G, I produce T, I lose something, but then maybe the rest of the problem is very easy on T. Okay? So overall, my approximation factor is basically what I lost in going from G to T. And otherwise, T was easy. Okay, so this is a very strong approach, the idea of trying to approximate an undirected graph with a tree, which is sort of like the simplest possible graph you can ask for. All right, so now how are we going to quantify our sense of approximating distances and stuff like that? Okay. So we're going to focus on a notion, I guess we'll call a stretch of an edge in the undirected graph. Okay. So let E be some edge from your original graph, right? So E was an edge from point A to point B, and you create some crazy tree, right? So now your path from point A to point B might be much longer than the original length of the edge, okay? And we want to limit how much longer. So the stretch is the ratio of the distance in the tree, which is presumably larger, to the distance in the original graph. Okay, so this should be bigger than 1, but we want it to be as small as possible, right? If it was 1 exactly, then actually you have a tree that exactly preserves all the edge lengths. That would be great. Okay, but that's probably not something we can ask for. And ideally, we would get stretch to be small, something like polylogarithmic in that. Okay, and hopefully that would translate to a polylogarithmic approximation bound for whatever one of those crazy problems you might have been interested in. Right? Okay. Interrupt me if you have questions. Interrupt me if you're upset. Any reason at all. It's fine. Okay. All right. Okay, so maybe one thing to ask for is, okay, can we come up with a tree, or let's say even for sake of concreteness, can we come up with a spanning tree that preserves, that has low stretch, something small, polylogarithmic, even square root n? Okay. Can we get low stretch for all edges simultaneously? Okay. Yeah. Mm-hmm. Yeah, so ideally we want for all the edges the stretch to be small, which is to say the maximum stretch should be small. Yeah. Okay. Okay, so we like to get all edges. That would be great, right? But here's a graph that presents an issue. Why? Yeah. Okay, so any spanning tree would delete one of the edges in the cycle, right? So I'll delete this one. Okay. That edge in particular now has stretch n, right? Or n minus 1, because it has to go around. Okay. So, okay, we can't actually ask for a spanning tree that'll give us stretch 1. Okay. Fine, fine. What if it didn't have to be a spanning tree? You can add edges. So you can build an auxiliary tree. Um, well, that's another idea that's sometimes explored, but will take us in a slightly different direction. So yes, in fact, whatever algorithm I present today, often the right thing is actually to make many copies of it as well. So that's a different idea, but let's focus just for teaching's sake on building one auxiliary tree. Oh, okay, so we can try. Okay, so let me add. Okay, well let's do it. So one is to turn this into like a wheel or something like that, right? Okay. Um, Let me add one more requirement then. I'm also going to say that, see, for spanning tree, this came for free because it's always a subgraph, so distances only go up. But if you're doing auxiliary trees, then you can add shortcuts and stuff, so distances can go down. So what if I told you that you had to have the distances go up and otherwise? Because stretch is not as useful if I can just add kind of like lots of shortcuts so that all the edges become small. So in other words, here's my issue, is that the opposite pairs uh, now have distance 2. And really the original distance was like n over 2 or something. So really we're still warping by a factor of n. It's just that here in stretch I only focused on overestimates, assuming that the distances go up. So if I was going to require that, then I would have to make all these edges of weight like n over 4 or something to make sure distances are big, but then your stretch is again n over 4. Yeah. Yeah? Okay, and what would the tree look like? Okay, so I can draw that. So maybe try to set up something like this. Okay. I hope it's even. Okay. I hope it's a power of 2. Uh, this kind of thing. Okay. Uh, good. I'm getting pretty lucky now. Okay. I don't know, something like this, something like that. Uh, so I guess one thing is that, so this is a good idea. And I'll mention two. This is very, and also looks great, to be honest. Uh, I'll mention two things. So of course, like an edge like this, which is paired up right away, is doing great, right? And that sort of motivates the construction, I think. The edge next to it is not quite so lucky because it has to go up because it's sort of sandwiched between two kind of moderately large subtrees. This could be addressed to some extent if we kind of randomly spin it to an expectation you don't get unlucky too much, and I guess that'll be implicit in what we do later. Another thing to point out is that we still have this kind of semi-issue of, oh, I can go across the circle now in much fewer edges, roughly log n edges, to go up the tree and down the tree. So what you might want to do is you might want to make these edge weights go up, kind of, so to speak, uh, bigger and bigger and down and down. So if I had done that and like labeled this 8, 4, 2, 1, I think you'll find that actually now the length from top to bottom is pretty close to n if you did it correctly and you went up in powers of 2 like that. Okay. Partly because when you go from one tree of height 2 to height 3, you know you're kind of going from one group of 4 vertices to the next group of 4 vertices, so that the distance should be at least kind of 4, so to speak. Okay, so this is actually a good idea, and you can see part of the expressive power of getting to introduce auxiliary edges. Right, you can do more than a spanning tree. All right, so what are some of the results that are known? Okay, so one thing is that in both examples, or in both attempts, it sort of becomes clear that, especially the cycle made clear, we're not going to get like a deterministic low stretch for all edges. Okay? So we need to relax a little bit. So there's two different notions. One is deterministic. I just want to introduce the result, but we won't discuss it in much detail. So the first sort of result in this line of work showed that you can find a spanning tree so that the average stretch over all edges, so I'm summing up the edges, their stretches, and then dividing by the number of edges. The average stretch is close to polylogarithmic, n to the little o of 1. Okay, it's like n to the 1 over log n or something like that. Okay. But still, this is a very surprising. It's also deterministic. It's based on a technique called region growing and low diameter decompositions, which we might emphasize in approximation class, but since it's not randomized, we will not discuss it. All right? But it's good to be aware of it. The one we'll focus on, it's actually a little stronger, is going to be a randomized dominating tree metric. I'll explain the dominating part in a moment. Or no, I won't explain it now, actually. But again, we're going to do an auxiliary tree. So I guess here blue was supposed to be the original graph, and then red is the auxiliary tree. And it's going to be dominated in the sense that the distances in the tree will be bigger than distances in the graph for the reasons we've already discussed. And it's going to be randomized, and for every edge E, the expected stretch will be small. Okay, so we can't guarantee that every edge will have small stretch, but we can guarantee that for every edge, the expected stretch is small. So we'll do a randomized construction, which will help address this issue of like unlucky edges that came up in our picture earlier. It'll also have another property. It'll be what's called a hierarchical tree metric. So for us, all the vertices are going to be at the leaves. The vertices from the original graph are going to be at the leaves. And then the above nodes are nodes we introduce when we build our tree. Okay. And it's going to have this nice structure where the edge lengths are going up geometrically. And just based on the height of the edge, or like if you're going from level 1 to level 2 or level 2 to level 3, that tells you the length of the edge. Okay, so this goes up in factors of 4. Okay, and this property is sometimes useful for some of those approximation problems. So not only is this a tree, but the shortest path metric is like very rigid, right? Like if I want to know the distance from point A to point B, I really just need to know where the least common ancestor is, because the biggest edge is basically the length of the path up to a constant factor, right? 16 dominates 4 plus 1. All right, so that's a nice property. That's just going to fall out naturally from our construction, but it does have some value. Okay, so, all right, so really the idea of building, the high level idea really starts in 96 and 98 by Bartal. And he was able to get the stretch, that expected stretch for each edge, to log n log n. Okay. And what he did was very similar to what we'll study today. Okay, and then that led to bounds for many problems at once. He also helped make the connections or highlight why tree metrics are useful, that conceptual connection. Okay. And then a follow-up paper a few years later was able to go from log n, log n, and get rid of that pesky log n, and get log n bounds for all sorts of approximation. And log n was known to be the lower bound as well. You can't do better than log n. Okay. All right, so sometimes these are called Bartal trees, even though the final result is by this group FRT. All right, so what's the theorem? So we're going to describe an algorithm that produces a dominating tree metric, a hierarchical dominating tree metric, where for every edge, the expected stretch is at most log n. Okay, that's what we'll show today. All right. Any questions? Because we just went through a lot of definitions in a brand new model. Okay. All right. So I nicknamed this algorithm Scoopity Whoopty Scoop, but that's not its real name. I don't know if it has a real name. But let me explain what the algorithm does. So the idea is we're going to like randomly carve up this graph. So imagine these are just points and say the distance on the projection is roughly the distance between the 2 points. Okay. And we're going to sort of scoop up the graph and keep dividing it up. So, okay, so first of all, let's say that the diameter of this graph is d or something. Okay. And what we're going to do is we're going to carve out balls of size like d over 4, something close to the diameter, centered at points, but the points are ordered uniformly at random. So let's say that this is like maybe that's like d over 4 or something in radius or diameter. Okay. So the algorithm will go through vertices random order. Maybe it'll be centered here. Maybe this is the first vertex. Okay. It'll kind of scoop those out. And then I don't know what the random second vertex is. Maybe it's this one. Okay. And it'll scoop out a ball of the same radius like that. Okay. And then whatever the third vertex is, let's say it's this one. It'll scoop out a ball of that radius. Now here we actually have some overlap, right? So the ones that are already scooped out don't get scooped out again. So get something like that. Okay, like that. All right. And then whatever's the next vertex in random order, maybe it's that one. We scoop out another one. Okay. And again, there's some overlap. Okay. And gradually you'll scoop out all the points because you'll just go through all the points in some random order. Okay, fine. But then you're going to keep doing that with balls of smaller and smaller radii. Okay, so the next time you have something that'll go down by another factor of 4. So I'll do a different color. Okay, something like that. And it's going to go through the points in the same order. Something like this. Yeah. We use the same ordering. And then you'll end up, and then you do the scooping thing all over again. And you'll end up kind of overlaying the point set with a bunch of now green circles until everything is covered. And so forth. And you just keep, yeah. And so you keep repeating the scooping procedure until at the end, like the radius is very close to 0 and all the points are just by themselves in little circles. Okay, so you'll end up creating all these layers. All right. Maybe something like this. Okay. And we're going to use that and sort of use those pieces to arrange it in a tree. Okay. So, at some level, so the edges on the tree are sort of reflecting the radii of those circles. Okay. And I know if a set of points is within distance 10, I mean, they're all in the same circle of radius 10, then they're all in distance at most 10. So that sort of motivates it. Okay, so that's the high level idea, is that we kind of scoop out all these points with geometrically decreasing radii, centered at points, drawn in random order. So it's kind of a crazy algorithm. And we use those clusters to arrange the points and build a tree. That's the high level. Let me give it a little bit more detail so it's more concrete what we're analyzing. You'll probably want to ultimately look at the nodes closely to sort it out because it's a bit magical. So, okay, let's let d be the diameter. Okay, and the number of levels will be log base 4 of diameter, partly because we'll start at radius 1 and we'll go up to roughly d. Okay, and we're going in factors of 4. So all the randomization occurs in step 1. You do 2 things. You order the vertices uniformly at random. Okay, and I'm going to choose some factor alpha between 1 and 2, uniformly at random. What that's going to do is going to kind of shrink or expand the radii just a little bit. Let me explain. If we look at step 2, this is where I'm doing the scooping. Okay, so in the top step, I equals L or something. So I'm scooping balls of radius alpha times 4 to the I minus 1. Right, so at the top level, that's like d over 4, roughly. Okay, except it's randomly stretched by this factor alpha. So it's not exactly d over 4. It might be a little bit bigger. It might be a little bit smaller. Not too much, only a factor of 2. But that little randomization kind of helps with avoiding certain bad luck in the analysis. And it'll scoop them out in order. And then you're going to build, kind of build this laminar family of sets based on your scoops, your clusters. So, okay, the idea is that to actually build this tree, we're going to associate each node in the tree with a subset of vertices. So the root will have the entire graph, all the vertices. Okay. Now, but the inductive case is, okay, I have a node that has some set of vertices, might have been the root with all the vertices, and it's going to have children. Okay. And so what I'm going to do is I'm going to go to the set of clusters of the next level, the smaller circles, and every time I find a cluster that intersects with the set up above, I'll put that intersection as one of the children, and then I'll go through all the clusters this way. Okay, so I have some subtree or some root of a subtree that represents a set of nodes, and I go through a set of clusters of the appropriate level, and the intersecting sets will give you the roots of the next level of subtrees. Okay. All right, so a little delicate. Okay. Yeah, and maybe it's worth pointing out, I think the main difference between Bartol's paper, which got the log n factor, and the FRT paper that got the log n factor, is that in Bartol's paper, for every level, so I equals L minus 1, L minus 2, L minus 3, it does a new random permutation. It reorders the vertices. Okay, and that led to a log n bound. And somehow, if you just order the vertices once at the beginning, you stick with it, you get rid of the log n factor. Okay, so yeah, these things are very subtle. Okay, all right, so that's the algorithm. All right, it remains to analyze it. Any questions? All right. Okay, so let's fix a pair of vertices. We need to show that the expected distance between them is at most a log factor times their original distance. Okay. All right, so let's set this up. I thought I erased. Did I erase this? No? Okay, fine. All right, so let me introduce some notation. All right, so at some level, the height at which the two vertices are split up by some scoops, that sort of tells you where they finally branch off into subtrees. Okay, so if they're grouped together, they're going to be in the same subtrees, and then finally they're split apart. Okay, and because it's a hierarchical tree metric where it's always going up in powers of 4, really what level they got split apart roughly determines their distance. Okay, so if they get split up at height k, their distance is roughly 4 to the k. Maybe it's 2 times 4 to the k plus some smaller factors or whatever, but up to a constant, it's 4 to the k. Okay, so okay, we're going to focus on the height at which they're split up. Now, when they did get split up, they got split up by some scoop or some cluster that was centered at some vertex W. Okay. In that case, I'll say that W contributes 4 to the k to the tree distance. Okay, so really only one vertex in a particular random outcome will contribute to the distance. So W is sort of responsible for assigning 4 to the k to dtuv. Okay. So up to a constant at least, we can write the distance from u to v as summing over all the vertices, how much did W contribute to the distance in that sense of the word? That's how we'll frame it. All right, so here is the claim. So this is where we're going to do most of our work. So we're going to analyze, a particular vertex W and how much it contributes in expectation. But we're going to focus, it's going to be parameterized by kind of its ranking in terms of distance from U to V, right? So U and V are the closest vertices to U or V, okay? And then when I say like the third closest point, I mean like the minimum distance between this point and V or U, okay? So just the closest to either of them. So let's say that W is the Lth closest vertex, okay? The claim that is that the expected contribution from W to the distance is at most 4 times the actual distance divided by L. Okay, so in other words, we're saying that the vertices that are further away from U and V, we expect to contribute less to the distance. It makes some intuitive sense because you would think that the vertices that are very close to U and V are more likely to scoop them out. But of course, that's not even close to a full argument. Okay. All right, so before proving this, why is this useful? All right, let's say this claim is true. There's some expected contribution that's decaying in sort of the ranking. Why does that give me the bound I seek? Yeah, okay, so spell it out for me. Okay, so we want to analyze expected distance UV, right? Okay, what comes next? Yeah. Okay, in particular, I think in reference to this, so we'll sum over all the vertices W, the expected contribution from W. And so what we're going to get then is summing over all L from 1 to N, 4 times the 2 distance of 1 over L. And that's our favorite harmonic sum. So we get log n times duv. Okay? Good. So that's why this claim will give us the overall result. Great. Okay, so now we just need to prove this thing. Okay. Now I have 2 points U and V, and W. Yeah. Sure. Yeah. We can go through the analysis and see if it's an issue. My laziest explanation is like, oh, let's just randomly perturb the points a little bit, right? If I added the tiniest decimal point to all the distances, nothing really changes, and you'll have no ties. And you don't actually have to do it. You can just pretend to do it, in which case you're breaking ties arbitrarily. So I guess that works. Okay. Yeah, it shouldn't be an issue. All right. Okay. So you have 2 points U and V. W is somewhere. And U and V. And I'm going to assume that W is closer to U. Okay, henceforth. So that distance from W to U or V is really distance from W to U. All right, so I think, as usual, the most important part of the analysis is the first step to frame it correctly. So how do they frame it? Well, we're going to define two events that have to occur in order for W to contribute to the distance. So the first event is that, okay, so there's U, there's V, and there's W, where W is closer to U. Okay. So in order for a cluster centered at W to split them up, that radius needs to be between the distance from W to U and W to V. Okay. So the radius is alpha 4 to the k. Okay, for some k, for any k. Okay, but it's saying that the radius at some level has to fall in this interval for W to possibly split them up. So that's one necessary condition. The second necessary condition is that W is ordered before any of the points that are closer to U or V, right? Because if another point is closer to U or V and is ranked earlier, then W will always be scooping out U and V, or U or V, but at least one of them, before W has a chance to split them up. Okay, so if it's the 10th closest, then it's got to beat out 9 other points to have any chance at being the vertex that splits them up. All right, so those are our two events. All right, so what are some funny things? Question, are E1 and E2 dependent on each other or independent? Yeah. Why? Right, so E1 actually only depends on alpha. Everything else is fixed, right? The distances from W to U and W to V, that's part of the input. And the second one only depends on the random ordering, which has nothing to do with alpha, right? So that's something very clever that has happened, because it's always nice to you take a step back. We're analyzing a completely crazy algorithm, right? And so the idea that you can identify two events that you can even analyze separately is already a huge start. Right? It's not easy to analyze something like this. Okay. Now, of these, yeah. Um, are they sufficient? Um, we don't need them to be sufficient. We don't require, and I think they're not. But yeah, I think that's why I only focus on necessary. All right, so we have two events. The first event is a little harder to analyze. That'll be most of our work. The second event is relatively easy. What's the probability of event 2 happening? 1 over L. Okay. That's all we're going to say about event 2. Tough part is event 1. Okay, so we're going to really have two cases in our analysis. One case is where the distance between U and V is bigger than the distance from W to U. Okay, that sort of is saying that any cluster that from W that splits them apart. So the distance between W and U is relatively. Think of W being very close to U and smaller than U to V. So if there's a cluster that splits them apart, this distance is not very big compared to the distance between U and V. So it's not really a major issue. That's not a high risk thing. We'll go through the calculations. The more interesting case we'll spend more time on is when here's U and V and W is potentially really far away. Okay, in which case that if W does split them up, right? This is a huge cluster and assigns a big distance. So this is the risky one. All right. All right, let's do this case carefully. Okay, so just choose any k that satisfies E1. So we're going to analyze the contribution in this case. Okay. All right, so what do we know? We know that 4k plus 1, right? So I know that dWv is less than or equal to 2 times the distance from W to V, which by the triangle inequality is at most 2 times the distance between WU and UV. And then I know that the distance from WU is small compared to UV. Okay. Okay. So, okay, so what's kind of going on? So you have U, you have V, and presumably W is very close to U. Okay. So if we have something that falls in this range, then the circle is going to be relatively small compared to U and V, and that's what we see play out. So this radius, which is an upper bound on the distance that we give, is at most a constant factor bigger than the distance from U to V. Okay. All right, so that's all we wanted to show. Fine. Okay. Let's look at the more interesting case. This is where W may be rather far away in the bad case, in which case a cluster centered at W that goes through them will be quite problematic. Okay. So here we'll have to show that hopefully the odds of this happening will be small. Okay. Does anyone want to try to guess some high-level intuition? So let's say that W is really big, so that it could fall in between. There's kind of one ingredient of our, yeah. So okay, so if this was like 4 to the k distance away from W, then alpha to 4 to the k, or 2 times 4 to the k, which is the maximum range for alpha, and alpha is somewhere in the middle, right? So once the distances get really big, then that alpha factor starts to really help you. So if you have this like huge clumsy thing, then perturbing it by a factor of 2 may take you way out of that splitting range. Okay, so that's sort of the intuition, is that when you're in this high risk situation where radius is much bigger, also 2 times 4 to the k, it takes you way out of the range, so that the margin of alpha being in the middle is smaller. Okay, but now we have to do some calculations and hope it cancels out and offsets each other nicely. But that's the intuition. So one technicality to address is that the choice of k is unique, which might seem implicit in the pictures, but is not a given fact, right? So we just need to establish there's only one possible choice of k. Again, here the intuition is going to be when the distance is much bigger than uv, and if some value, if alpha 4 to the k falls in, then multiplying by 4 should take you way out of the range, and dividing by 4 should take you way out of the range. Okay, so we have time, so that's okay. All right, so if you wanted to, okay, so let's say that there exists some alpha between 1 and 2 and some choice of k that does fall in the range. I want to show that if I went to the k plus 1 range, any choice of alpha couldn't possibly fit in. And if I moved to the k minus 1 range, any choice of alpha couldn't fall between. Okay, so this should just be an exercise of triangle inequality as usual. Okay, so we would have the distance from W to U is at least, so this is sort of rearranging the triangle inequality. So we're really applying the triangle inequality to distance WV, which is at most going from W to U, then W to V. We subtract it and put it on the other side. Okay. So what do I know? I know that this is at least 4 to the k. Okay. And this is at most 4 to the k over 2. Oh, am I doing k minus 1 first? Okay. We're doing k minus 1 here. Sorry. Okay. Okay. Let me do this right. 2 times 4 to the k minus 1, which gives us 2 to the 4 to the k minus 1. Okay, so distance from W to U is always bigger than 2 to the 4 to the k minus 1. So if I went down to k minus 1 and I made alpha as big as possible, it still wouldn't fit. Okay. For the k plus 1 case, should be the same. If I look at the distance from W to V, okay, this is at most, by a triangle inequality, going from W to U plus going from U to V. Okay. And okay, I know that going from W to U was at most 2 times 4 to the k minus 1. Okay. And I know that DUV is no bigger than DWU. I would have liked to get a strict inequality, but it shouldn't be a big deal. Okay. Which is at most 4 to the k. Okay. So I don't know if there should be a better way, but if I change the algorithm so it's choosing a value strictly between 1 and 2, then okay, we're okay. All right. Yeah. Well, it says that if the so it says that there could only be one choice of k, but there could possibly be no choice of k. So if W is like not the right distance, it's possible that any choice. So if W is okay, so what are we saying? We're saying that between 4 to the k and 4 to the k plus 1, and then we have 2 times 4 to the k, right? So alpha is something in this range. But if the actual distance was in this range, then actually no choice of alpha would let them split up. So it could be that there's no choice of k that works. But if there is a choice of k, there's only one. I guess that's what I meant when I said unique. So I sure wrote if exists. All right, good. That's really more of a formality. Okay. But it makes the analysis kind of clear, right? Now we only have to focus on one k if there is a k. So we should assume there is a k. Otherwise, it's going to contribute nothing. That's not an issue. So to assume there is a k, it's now fixed, so I can kind of refer to k unambiguously as the k that would split them up. All right, how would I analyze the probability of event 1? think of this like as a line. U is at 0. No, sorry. W is at 0. U is at dWu. V is at dWv, right? And we're going to choose some value uniformly at random from some interval between 4 to the k and 2 times 4 to the k. Right? Okay, so I'm throwing a dart somewhere in the blue region, and event U1 occurs if it falls into purple. Okay, so let's just write that out as a fraction. What's in the numerator? And what's in the denominator? Denominator, put 4 to the k, right? Because that's the width of the blue. What's in the numerator? Okay. Yes, but we'll take a baby step to get there. So if I was just working off of the picture first, it would be dWv minus dWu, right? Okay, and how do I clean this up? Triangle inequality, which, as just suggested, will give us duv over 4 to the k, right? Okay. That means, and then not only that, so in other words, if E1 and, okay, so in order to contribute, E1 and E2 have to occur, right? E1 occurs with probability the distance divided by 4k, and if you contribute, you add 4k, 4 to the k, roughly, right? So the 4 to the k's will cancel out. So, right, so if we have all that put together, okay, so first the choice of k is unique. So if there's a contribution, you pay 4 to the k, and you have to have E1 and E2 occur, right? Which we now know can be taken separately. Right? And what do we show? For E1, we got distance UV divided by 4 to the k, and then we got 1 over L for E2. Possibly this should have been k plus 1, I don't really remember. Okay. Everything cancels out nicely. 4 times the distance between them divided by L, like we wanted. Okay. So somehow this magical algorithm works. Okay. All right, good. So that is then the analysis of how you get expected stretch log n, and that leads to approximation algorithms for a whole family of problems. For each one you have to show that this is the right kind of approximation, but it's not so tough. Well, maybe it depends case by case, but some of these are more clever than others, and so forth. Okay. All right, then that's it. I finished early so that you have 5 extra minutes to work on your homework. All right. Thank you.